Welcome to this lecture video. In this video, I am going to explain material science and semiconductor physics, which comes under module number 5 of engineering physics prescribed by VTU. Here, I am going to explain the following points. So, the energy level diagram for metal, semiconductor, and insulators, conductivity of N-type semiconductors, conductivity of P-type semiconductors, and expression for electrical conductivity of a semiconductor, and expression for electron and hole concentration. So these are all the topics going to be discussed here. First, let us look into energy level diagram for metal, semiconductor, and insulator. So here is a picture showing you the energy level diagram for metal, semiconductor, and insulator. So in the diagram here we are going to plot a graph of energy of electrons at different levels. So first let us consider metal. In metal we come across first we have to look into the atoms of metal. So in an atom we can see valence band as well as conduction band. The electrons which are present in valence band are known as valence electrons, and those electrons in the conduction band are known as conduction electrons. So here the valence band is overlapped with the conduction band. So this is observed at any temperature. So at any temperature, whenever an electric field is applied, the metals conduct electricity because electrons are already available in conduction band. So there will be a overlapping between valence band and conduction band. That's what observed in case of metals. Now let us look at the case of semiconductors. So in case of semiconductors, there will be a small gap between valence band and conduction band. The energy gap is observed to be around 1.1 electron volts in case of silicon and around 0.72 electron volts in case of germanium. So at lower temperature, semiconductors behaves like insulators. So electrons cannot gain energy and go to the conduction band. Whatever may be the potential difference is going to be applied. When you raise the temperature of semiconductor, the electrons present in valence band gains energy and reach conduction band and available for conduction. And the number of electrons reaching conduction band goes on increases as you keep on increasing the temperature. That's why the conductivity of semiconductor keep on increases with increase of temperature, because more and more electrons gain energy and reach the conduction band. But in case of metals, as you rise the temperature, due to thermal agitation, chances of collision of electrons with the lattice point will be more. That's why the resistance offered by the metal for the flow of electrons keep on increases. That's why in case of metals, as you rise the temperature, the resistance of the material increases. That is because of the thermal vibrations going to happen in case of metals. And hence the electrons interact with the metal ions, and hence resistance is come into picture for their propagation. Now the another class of material is insulator. So insulators are having a large energy gap. So energy gap is observed to be very large between valence band and conduction band. So here no electrons available in conduction band at any temperature. All the electrons are present in valence band only. Even though if you raise the temperature or applying large potential difference, the electron cannot reach the conduction band. Therefore, at any temperature, insulators will not conduct electricity. That's what the reason. So this is what about the energy level diagram in case of metals, semiconductors, and insulators. Now let us look at the conductivity in case of N-type semiconductors. First, let us look at semiconductors. So intrinsic semiconductors are pure semiconductors, and The number of electrons and holes in case of intrinsic semiconductor is observed to be same. Suppose if a semiconducting material is added with some impurity, then it is considered as an extrinsic semiconductor. If a tetravalent semiconducting material doped with pentavalent, then it is turns into a n-type semiconductor. So in case of n-type semiconductor, electrons are majority charge carriers and holes are minority charge carriers. That's what the observation made in case of n-type semiconductors. So the conductivity in case of n-type semiconductor is the sum of conductivity due to electrons and conductivity due to holes. It is observed that conductivity due to electron is given by Ne into E into mu E, where Ne is number of electrons per unit volume of the material, E is charge on the electron, and mu E is the mobility of the electrons. Similarly, conductivity due to holes is given by NH into E into mu H, or N hole into E into mu hole. Okay, so the total conductivity of n-type semiconductor is given by Ne into E into mu E plus NH into E into mu H. It is observed that the majority charge carriers in case of n-type semiconductor is electron. That's why number of electrons per unit volume of the material, that is Ne, is greater than Np. Here Np is nothing but number of holes per unit volume of the material. So here Ne is very much greater than Np. That's why the second term in this equation is not at all taken into consideration. So the conductivity in case of n-type semiconductor is given by sigma E is equal to Ne into E into mu E. So this is what the expression for conductivity in case of n-type semiconductor. So here the electron concentration is very much greater than that of hole concentration. That's why the second term here is not at all taken into account. Now conductivity of p-type semiconductors. So if a semiconducting material is doped with trivalent material, if tetravalent semiconducting material is doped with trivalent, then it will be converted into p-type. So p-type semiconductor is also considered as extrinsic semiconductor. The conductivity of p-type semiconductor is given by, that is total conductivity sigma is equal to conductivity due to electrons plus conductivity due to holes. That is sigma is equal to Ne into E into mu E plus NH into E into mu H. So here it is observed that the number of holes per unit volume of the material is very much greater than the number of electrons per unit volume. That's why we can write Np is greater than Ne. So that's why the first term in this equation is not at all considered for deciding the conductivity of p-type semiconductors. Therefore, conductivity of p-type semiconductor is expressed as sigma H is equal to NH into E into mu H. Here the hole concentration is very much greater than that of electron concentration. That's why conductivity of p-type semiconductor is given by sigma H is equal to NH into E into mu H. So this is what about the conductivity of p-type semiconductors. Now if we want to arrive at an expression for electrical conductivity in case of semiconductor, so it is observed that in case of a semiconducting material, if it is an intrinsic means not doped with any material, it is observed that the number of electrons will be equal to number of holes. So here the current that is going to pass through a semiconducting material is given by I is equal to Ne into A into Vd, where A is area of cross section, okay, and Vd is drift velocity, and N is number of electrons per unit volume of the material, and E is charge on the electron. Further, the current density J is equal to I by A. So therefore the current density J can be written as NeVd. Further, for semiconducting material, the current density J can be written as Ne into E into Vd into E plus NH into E into Vd into H. Therefore, we can write for drift velocity, that is Vd is equal to mu into E, where mu E is nothing but mobility of electrons. Further, the electric field applied E is equal to J by sigma. Therefore, the electrical conductivity in case of intrinsic semiconductor is given by sigma is equal to Ne into E into mu plus Nh into E into mu h. In case of intrinsic semiconductor, already told that the number of electrons will be equal to number of holes. That's why the above equation can be written as sigma intrinsic is equal to Ne into E into mu E plus mu h. Okay. So here Ne is equal to Nh. Ne is equal to Nh. That's why we are taking Ne common. So that's what the expression for electrical conductivity of semiconductor. That is sigma intrinsic is equal to Ne into E into mu E plus mu H. Okay, where mu E is mobility of electrons and mu H is the mobility of holes. So this is what the expression for electrical conductivity of a semiconductor. Now here we are having an expression for electron concentration, that is Ne. Here electron concentration means number of electrons per unit volume of the material, that is number of free electrons per unit volume of the material, given by Ne is equal to 2 into 2 pi me star kt by h square whole to the power of 3 by 2 into e to the power of minus Ec minus of Ef by kt, where Ec is energy of the electron in the conduction band, Ef is Fermi energy, and K is Boltzmann constant, and T is the temperature. Further, H is Planck's constant. Me star is nothing but rest mass of the electron. So altogether, if you apply, that will gives you the electron concentration. So just you have to remember the electron concentration expression. There is no derivation from the point of syllabus. And further expression for hole concentration, NH is given by, that means number of holes available per unit volume of the material, given by NH is equal to 2 into 2 pi mh star kt by h square whole to the power of 3 by 2 it to the power of it is power of EF minus, that is EF minus that is EF minus EV by kt, where EV is nothing but energy of the electrons in the valence band. EF is Fermi energy, and mh star is nothing but rest mass of the holes, and T is the temperature, K is Boltzmann constant, H is Planck's constant. So this is also an expression that you have to remember from the point of exam. So there is no derivation part for the hole concentration NH. So this is what about the expression for electron and hole concentration. Thank you.